My name's Andy Thompson, and this is work that I've been doing in collaboration with Kevin Spear, Florida State, Mark Flexus, who's at Caltech, Michael Scharlock at JPL, Lana Schultz-Kressian, who's in Jacksonville University, and Ryan Schubert was a master's student with Kevin Spear. And so I'm going to talk mostly about some recent work we've been doing in the Bellingshausen Sea, but what I'm going to try to do is emphasize the importance of sort of the connectedness between the different shelf seas in West Antarctica and potentially different drivers of what I'll call the overturning circulation on the continental shelf. So what I'm planning for today is to give a little bit of background, and then the talk is broken up into two parts. One that talks a little bit about the connection between what's happening at the coast and a continental shelf break, and then a second part that sort of focuses more on coastal dynamics that's impacting ice shelf melt rates. I would very much encourage people to just interrupt me as we go along. I think it's nice to have some interaction during these remote presentations, so please don't hesitate to just stop me, and be happy to have some discussion. Okay, so I want to start by kind of taking a broad view of the oceanic circulation in West Antarctica. It's a pretty unique place. There aren't a lot of places in the ocean where you can say, this looks like somewhere else, but I think there are some really distinct aspects of the circulation and dynamical controls on what's governing everything from heat transport towards the ice shelves, exchange between offshore and continental shelf. And that's because this is really the confluence of some very different circulation features. And so I'm showing here a map of the Southern Ocean, looking down on Antarctica. And of course, the dominant circulation feature in the Southern Ocean is the Antarctic Circumpolar Current, eastward flow that goes all the way around Antarctica. And of course, when you get into West Antarctica, this is where the Antarctic Circumpolar Current, or the ACC, is closest to the coast, is closest to the continental shelf, as shown schematically by these white arrows here that are showing the different frontal currents of the ACC. At the same time, what really changes here is the reason why the ACC is moving closer to the continental shelf is you're moving to the east of a large gyre circulation, the Ross Gyre, which is shown here schematically in yellow, although we do think that the gyre here does have a structure that extends a bit further to the east, and fluctuations in this gyre circulation can certainly impact how much warm water gets near the shelf. And then that in turn is interacting with a separate boundary current that is flowing in the opposite direction to the ACC. We call this the Antarctic Slope Current, which is a near circumpolar feature situated pretty much right at the continental shelf break. And I'll talk about this a little bit more. We talk about it as a near circumpolar feature because it's quite well defined certainly throughout East Antarctica. And it's a little bit uncertain about where its formation happens, somewhere between the Bellingshausen and the Amundsen Sea. And I'll talk a bit today about what we think the mechanism is for that formation. Of course, then as you move up onto the continental shelf, there are some quite complicated circulation features that are strongly driven by bathymetry on the continental shelf that I'll talk about today. And there's a third boundary current that's actually not shown schematically in this picture, but will be a focus of today's talk, which is the Antarctic Coastal Current. And so you have all these different circulation features that have their own sort of inherent spatial and temporal scales of variability. And I think our understanding of how these different circulation features and how they interact with each other is still very much in stages of development. And our ability to sort of predict how they're going to change in the future is, I'd say, relatively immature right now. And of course, the motivation for this talk, here's another picture looking down on Antarctica. I noticed there is a message in the chat there. Craig, you can, if it's a question, I'm happy to, for you to just ask it.
It looks like someone has posted, someone posted your review paper.
Okay, awesome, thank you very much. So of course, everyone on this talk is probably quite familiar with the motivation here. People have seen plots like this one or similar. This is a nice figure from Sukhil Audusumili's thesis work, showing that, of course, when we look at variations in ice shelf melt rates, we're seeing the strongest melt rates in West Antarctica. And the argument for that is that there's stronger thermal driving in West Antarctica. And so if you look at the colors here, these sort of yellow to green colors around the continental shelf, you can see where the warmer water is getting up onto the shelf is predominantly the western side of the Antarctic Peninsula in through the Bellingshausen and the Amundsen Seas. And of course, what I really like about this figure is it shows some nice spatial variability as well. And if we think about what are again, the drivers of this changes in thermal forcing on the shelf, I'd argue that the dominant process that people have focused on so far has been what happens at the shelf break. So the transition from the continental slope to the continental shelf. And we know from decades now of hydrography and also modeling work structure of what we call the Antarctic slope front. So the frontal structure that forms, again, right at the shelf break, we know that it varies spatially in a significant way around Antarctica. And if we look in regions in East Antarctica, which is shown here on the left, we have a very strong frontal feature that really shields that warm water for getting up onto the shelf. You can see in color here is temperature. And these density classes that are hosting that warm, what we'll call circumpolar deep water, tend to outcrop on the slope itself and don't access the shelf. This can change in regions where either dense water is getting off the shelf. So for instance, in the southern part of the Weddell Sea, that lifts up those density classes that are hosting that warm circumpolar deep water, and that can ventilate the shelf. Or when we get around to West Antarctica, we saw that very strong thermal driving on the shelf. You can see that these density classes here that again are hosting that water now have access to the shelf. And if we think about what controls this spatial variability, again, the dominant mechanism that has been discussed in the literature has really been the influence of the wind stress at the continental shelf break. And so of course, when you get around East Antarctica, you have very strong easterlies that are aligned with the shelf break that help to set up this frontal structure, which is then of course enhanced by processes happening on the shelf. And when we look to West Antarctica, we have regions where those easterlies are weaker, or in some places can actually change direction and actually blow to the east, having westerlies. But I'd like to argue that there are other processes that are not just local to the shelf break that can be very, very important for setting the warm water that gets onto the continental shelf. And so I'm going to spend just a couple minutes going through this really nice picture that comes from Nature Geoscience paper by Adrian Jenkins and his colleagues. Again, I think people have seen images like this before. In the bottom right is a map of the Amundsen Sea showing the bathymetry. And we're going to specifically look here at hydrographic profiles that have been collected in front of the Dotson ice shelf, which is this blue region here. And on the left, I'm showing vertical profiles of temperature and salinity. And of course, the temperature gets a lot of attention because this is the water that's getting into these ice shelf cavities and melting the ice shelves. And there's very clear evidence that the shelf goes through these regimes where there are thick layers of circumpolar deep water, which are shown sort of in these green and blue colors, and then times different years where you have these thinner layers of circumpolar deep water, which are shown in the blue and the purple. But what I think receives less attention, excuse me, is changes in the salinity structure. And of course, because we're in polar regions, if we look at the equation of state, the density structure is really driven by the salinity and not by the temperature. Temperature is mostly a passive tracer. Of course, temperature is what's driving the ice shelf melt. So they're very strongly coupled. And one can sort of see here that there's also a change in the structure of the salinity. I think it's clearer if you look at this in terms of a temperature salinity diagram. So again, the colors here are showing thick CDW years and thin CDW years. And you can see the properties of the circumpolar deep water are not changing very much. We still have waters at about 0.5 degrees in this region. But what is changing is, in particular, the salinity of what we call winter water. Okay, so this other elbow here in the TS diagram, that's very indicative of waters that are forming through a combination of surface forcing in the winter, but also interacting with any meltwater that might be coming out of these ice shelves. And so we see a really dramatic change in the properties of winter water that are coupled to these times of the year, which are thick CDW and thin CDW years. And then the last figure I want to show is not one that's in Adrian's paper, but one that a student of mine, Ruth Morman, went away and looked at, is to actually look at the ocean's vertical stratification. So for oceanographers, what we call n squared, this is a measure of how the density is changing with depth. And we also see that in the upper part of the water column, there's a very strong modulation of the ocean's density structure that are related to these thick and thin years. And in particular, what you see is in times of years when that CDW layer is thick, you get a much stronger stratification between the winter water layer and the CDW layer. And in the years where that CDW layer is thin, that stratification has been eroded. And of course, this sort of makes sense. In those years where there's more melting, you may have more meltwater coming up that will help stratify the water column. And in those years where there's less melt, you have weaker stratification. But what I try to get to in this talk, the motivation is drivers that happen closer to the coast that could give rise to these changes in stratification and thus modulate the overturning circulation from the coast or processes happening on the shelf that are not necessarily connected to dynamics that are happening at the shelf break. So that's sort of the overlying goals of this talk. I'll try to address two questions. What is the combined role of both heat and freshwater transport on establishing both boundary currents that may involve interactions between different shelf seas? And also what I'll talk about in terms of transforming water masses, what we really mean by an overturning circulation on the shelf. And then the second part of the talk, we'll talk a little bit about this idea that there is mechanisms for significant exchange between the different shelf seas. So say, for instance, the Bellingshausen and the Amundsen that may impact ice shelf melt rates. Okay, so I'm going to sort of focus in this talk on the region we refer to as the Bellingshausen Sea. It's partially because this is the region that we've been doing some work in the last couple of years, so it's an area that I've thought about a lot. But I'd also argue that it has a quite important role in setting sort of the larger scale circulation of West Antarctica. And it's also a region where we have just spent less time making observations compared to other regions like the West Antarctic Peninsula, excuse me, and the Amundsen Sea. So here's just a map of, just to be clear about what we mean by the Bellingshausen Sea. On the upper right there, you can see that this is a region that is situated so to the south and the west of what I'll refer to as the West Antarctic Peninsula, located to the east of the Amundsen Sea. So it is sandwiched between two regions, what we have observed relatively well, simply the West Antarctic Peninsula, because we have a long-term ecological research program that has been going on there for decades now. And more recently in the Amundsen Sea because of the importance of melt rates we're seeing at Pine Island Glacier and Thwaites. The larger map here shows a better view of the bathymetry. I'll sort of talk about the Bellingshausen Sea as that region bounded by Marguerite Trough, which is to the east here, and then this region where the bathymetry gets shallow sort of marks this eastern boundary to the Amundsen Sea. Like most shelf seas in West Antarctica and really throughout the Antarctic continental shelves, the bathymetry is dominated by glacially carved troughs. And there are two major troughs in the Bellingshausen Sea, the Lataty Trough here and the Belgica Trough, that provide conduits, if you will, for warm circumpolar deep water to move from the shelf break towards the coast and ultimately to floating ice shelves. And I've labeled some of the floating ice shelves in the Bellingshausen Sea here to the south. And I've mentioned that this is a region where we don't have a lot of observations. I'm actually on here have indicated CTD positions of two fairly substantial fields in the last 20 years or so. A really important program was carried out by the British Antarctic Survey on the James Clark Ross in 2007, or the yellow dots that you can see here. Really remarkable set of hydrography that we have been working on in collaboration with some colleagues at BASS. There's a couple of these sections spanning these troughs completely. And in the red dots here, we're showing CTDs that were collected during a more recent research cruise that was I was a part of in 2019, where we were able to sample across some of these troughs and also made it into close to one of the ice shelves here, Venable Ice Shelf, that I'll talk about in a minute. These orange lines here are ocean gliders that we deployed on this field program. I won't have time today to talk about those very much. I do just want to indicate that we did deploy gliders in 2020 as well, during a time of year when or at least a year when the sea ice extent was much closer to the coast. than when we were there in 2019. And so for some of the stuff I'm talking about here, we're going to look at the frontal structure at the shelf break off to the west of the Belgica Trough. And we have this new data set that we are really just starting to dig into here. So let me start by giving a bit of an overview of what the hydrography looks like on the continental shelf here in the Bellingshausen Sea. I'm showing on the left here a map. This is the Belgica Trough. This is the Leyte Trough. And I'm just showing sections here of temperature across both these troughs in red on the top and in blue on the bottom. And this is a structure that I think most of us are familiar with. You can see here that the warmest water is not located at the surface, but it's flowing in at depth. This is this modified circumpolar deep water. And we can see that this warmest water sits very much on the eastern side of the trough. You have this warm water coming in. You can certainly see that coming in the Leyte Trough as well. And if you look at the density structure, which is shown in the black lines, I'm going to come back to this in a minute, you can also see an interesting change on the western side of the trough, where this winter water, remember that's the, I showed that water mass in the TS diagrams from the Jenkins paper. And we see this winter water layer being much thicker on the western side of the trough than on the eastern side. And so you start to see a suggestion here, at least, of this warm water coming in toward. You have cooler water that's potentially leaving and some modification of the winter water here. And that's very much confirmed by the velocity structure. So I'm showing those same sections across the troughs here, but now I'm showing velocities that are geostrophic. I'm sorry, these are the velocities that were collected from a lowered ADCP. So these are direct velocity measurements. And the color scheme here is such that if you see blue colors, that's water coming towards you. Red colors are water moving away from you. And again, if we focus here on the Belgica Trough, you have a signature here of waters coming towards you on the eastern side of the trough and flowing away from you here on red. And I've contoured here in black the temperature structure. And you can see that this warmest water, this tongue of modified circumpolar deep water, is flowing in, and these colder waters are flowing out. That's true close to the shelf break and also as you move further inshore. And in fact, closer to the coast, you have both of these troughs sort of hosting a cyclonic circulation where there's flow on the eastern side of the trough and flow out on the western side, both in the Leyte, the Belgica Trough. So there's very much a signature that I think is consistent with many regions on the continental shelf, that these troughs, through bathymetric steering, conservation of potential vorticity, support cyclonic gyre-like circulations within each trough. And that's very much a picture of the horizontal circulation, which again is confirmed with these depth average currents here, these arrows. But this also implies that there is a degree of vertical circulation. So an overturning circulation whereby these waters are coming in one density class and leaving in a second density class. And what's giving rise to that overturn in density space is the transformation of that warmer water into lighter waters via ice sheet. And to sort of support that argument, what I'm showing here are two sections from which we've calculated meltwater concentrations. I'm showing one here that is across, again, the Belgica and Leyte troughs, but I'm also showing a new section here that is very close to the Venable Ice Shelf. And so let me start with this one here in the southern part of the Bellingshausen Sea. This is depth on the y-axis. At the top here is the station number, where station 37 is the one closest to the coast. And what you see is a really distinct tongue of meltwater that starts around 150 meters depth, which is very well correlated with what we think the draft of the ice shelf face is in the Venable Ice Shelf. And one can see that this actually spreads here along a temperature surface, which actually is well correlated with the density surface. And so it's spreading out on a density surface, actually becoming shallower as you move along, and then flowing out back towards the shelf. As we move further away from the coast, we can see that that meltwater signature is much stronger again on the western side of the trough. So we see that in stations sort of 30 through 33 here. That's also somewhat true in the Leyte trough, that the meltwater concentration is higher to the west and lower to the east. with reduced meltwater on the eastern side of this trough. Interestingly, there are sort of 2 tons of higher meltwater concentrations here. Because of sort of the sparsity of the observations on the shelf, we've speculated here that these water mass signatures may actually come from different ice shelves, and thus are sitting on different density classes. But that's a little speculative at this point. And so the picture here now is that we have this warm water flowing into the coast. It's going into the ice shelf cavity. You see these enhanced meltwater concentrations on the western side, which the velocity structure said was flowing back towards the coast. And I'll show these last sections now of meltwater, which I think are quite interesting in terms of where does this meltwater go. And now I'm showing sections that are not on the shelf, but rather are perpendicular to the continental slope. One on the eastern side of the Bellingshausen and one on the western side. So again, we have depth, we have distance on the x-axis. This gray shading here is the continental slope. And so you see a very distinct picture where obviously there's a lot more meltwater on the western side of the Bellingshausen Sea here as compared to on the eastern side. But more importantly, we can see that all of that meltwater gets delivered back to the shelf and actually out to depths where the water column is almost 2,000 meters deep. And what it does when it flows out here is it forms this very strong frontal structure. And I'm going to show in a minute what this frontal structure does in terms of the velocity over the continental slope, and thus sort of the boundary currents at the continental slope. But to sort of summarize, the picture we have is that both of these troughs, again, provide a way for the warm water to come into the coast, but then that meltwater gets collected, and we think it gets collected all throughout the Bellingshausen Sea. Because the bathymetry is very shallow to the west, almost all of this meltwater gets delivered to a very discrete location on the western side of the Belgica Trough here and establishes this frontal structure. And we can see that a little bit more clearly here now if I show both the temperature and the salinity distribution. Again, this is on the western side of, if I just go back for a second, it's this orange section. So on the western side of the Bellingshausen Sea and just to the west of that Belgica Trough. We can see that this warm circumpolar deep water sits offshore, but we have this, I almost call it a wedge, this thick layer of winter water that I'll show in a minute is correlated with the glacial melt, flowing off the continental shelf and establishing these strong frontal structures here over the continental slope. Again, we're in a region where the density is largely driven by salinity. So again, you can see that this relatively fresh water is coming out and giving rise to lateral density gradients that will give rise to geostrophic currents. And this final picture on the right here is showing the relatively complex velocity structure over the continental slope. So the sign convention here that where this is positive or red, it's flowing into the page, which would be to the east, back towards the Belgica Trough. And where it's blue or negative, that water is flowing to the west, away from the Bellingshausen Sea and actually towards the sea. And so you'll notice that in particular, both in the deeper part of the continental slope, but also near the shelf break, you have a very strong vertically sheared velocity field. And so this, you have geostrophically balanced thermal shear, and that has to be driven by these horizontal density gradients. And so what we've argued is it is this delivery of this warm circumpolar deep water, delivery of this glacially modified winter water, this meltwater that comes out at the shelf break here, that establishes this density gradient and supports a westward flow, which we take to be the first instance of the Antarctic Slope Current in West Antarctica, which is then has been observed as we move westward towards the Amundsen Sea, and certainly when you get past the Ross Sea into eastern parts of Antarctica. So I think what's interesting here is that this suggests there's a degree of control over what the shelf break frontal structure looks like that doesn't have to just be due to the wind stress at the shelf break. That if there were anomalies in different years, for instance, or potentially even in seasonal timescales, where you modulated the delivery of winter water to the shelf break, that could feed back on the frontal structure there at the shelf break. And I'll just show that one other way. This is probably mostly for the physical oceanographers here. You can deduce a lot about what's happening from looking at properties in temperature and salinity space. So I'm showing 3 separate temperature salinity diagrams that are again taken from the continental slope. So there are 3 here, which is west, central, and then 1 here on the eastern side of the Belgica Trough. And the signature of a front in this temperature and salinity diagram space is a gap in the properties. And so a traditional place you would go to look at for frontal structure would be in the Circumpolar Deep Water class. And you can see here, both in the west and the central sections, there is indeed a strong front where there's warmer water offshore, these blue colors, and modified circumpolar deep water on the shelf. As you move to the east, that front's still there, and eventually it goes away where circumpolar deep water is getting up onto the continental shelf here. But what's striking is that there is also a frontal structure in winter water, and it only shows up in that western section. If I look again at this elbow here, where you have your cold but relatively salty water, this winter water, no signature of front pretty much all along the continental slope to the east. But if we get right to that place where that meltwater is delivered, we see that strong front. And interestingly, on the shelf, that winter water is actually a little bit saltier than what we have offshore, despite the fact that it is modified by glacial melt. And so if I sort of summarize what we think is happening here over the continental shelf, and in particular in terms of the initiation of the Antarctic Slope Current in the Bellingshausen Sea, it is that there's really 2 different types of circulations that are happening here. There's one that has been talked about in other shelf seas where this warm circumpolar deep water gets up onto the shelf. It is steered by these troughs into the ice shelves where it's modified into a lighter density class and flows back out towards the shelf. But we also believe that this salty signature in the winter water is some indication that there are coastal waters, and we'll talk a little bit in a minute about this coastal current that's flowing in, that are also being converted into winter water during winter months, largely due to the formation of sea ice. And so you have actually 2 different circulations, both cyclonic, but one that's taking relatively light surface water and converting it into winter water, and another taking denser circumpolar deep water and converting that into winter water. And so what I'm trying to show schematically here is what these circulations look like, not necessarily in depth latitude space, but in density latitude space. And so if I look on the y-axis here, this is potential density. Have surface waters that are flowing into the Bellingshausen Sea from the West Antarctic Peninsula. Through formation, they're becoming denser, filling this winter water class. And at the same time, we have denser water flowing onshore, being lightened through interactions with the ice shelves and filling this same density class, giving you this, again, this wedge or this thick layer of winter water. Corresponds with low potential vorticity for those who like to think about this in terms of dynamics. That again, because of the bathymetry, is delivered back to the coast and initiates this boundary current at the shelf break. So one of the things that this diagram tries to suggest is that we can think of the overturning circulation a little bit in terms of sort of what's being converted in a latitude space, but both of those transformations really involve a complicated delivery of that water towards the coast through much broader horizontal circulations. And the idea here is that we're trying to couple these horizontal circulations to overturning that is happening, again, in either depth space or in density space. And one aspect of this that, again, I think has received less attention is what's happening here at the coast to sort of enact these modifications. So that's sort of the first step, really focusing mostly at the Bellingshausen Sea. The implication of initiating a westward flow here on the western side of the Belgica Trough is that properties that are formed in the Bellingshausen Sea could be delivered into the Amundsen Sea and modify the properties that are that have access to, say, Pine Island Glacier and Glacier in the Amundsen Sea. So that's kind of the first part of the talk. For the second half or the remainder of the time, I'm going to focus now a little bit more on what's happening closer to the coast. So maybe I will pause just briefly to see if there are any questions before I continue.
I have a question.
Yeah.
So that was a really nice presentation about the beginning of the ASC. Do you have any thoughts on why the ASC stops upstream of where you're talking about?
How far, Steve, specifically are you thinking? You mean all the way at the end of its route in the Wood-Elsie or in the Amundsen?
Um, well, it stops, I guess, around the around the Antarctic Peninsula. Am I correct?
Oh, that's right.
So, what is the reason for it stopping? Why is there a gap in the coastal current? Not
Oh,
the
I'm
coastal
sorry.
current, but the slope current.
I'm sorry. I was thinking you mean upstream, not.
Okay, upstream. Yeah, I'm sorry. I always get
Yeah, no, no,
backwards.
no, that's fine. So I think this will get what I'm going to talk about now.
Okay,
So if we think about, I started with that picture of the thermal forcing, where circumpolar deep water starts its trajectory or its pathway through West Antarctica is on the West Antarctic Peninsula. It is a place where the ACC is closest to the shelf break, and therefore that's where it's the warmest. Where you're going to modify that warm circumpolar is at the coast. And what I'm going to argue next is that as that water gets up onto the shelf, it does flow into the coast, but it collects in a coastal current and flows all the way down through the Bellingshausen Sea. And it is only when you can deliver that modified water back to the shelf break that you initiate the ASC. So the reason why it is not along the Antarctic Peninsula is that the shelf properties are communicated back to the slope to establish that frontal structure there. There's essentially a cyclonic circulation that happens, which is the ACC into the shelf and being delivered southward along the coast.
great. All right, thank you. Very nice.
Uh, Thanks. I think Rachel looks like she's unmuted. Did you want to ask a question, Rachel? There are a few questions also in the chat I will get to.
Okay. Rachel, did you want to ask a question?
If not, we'll jump to some of the questions in the chat.
Okay.
Dan, would you like to ask your question? Or I can read it off. Sorry to pick on you if you don't feel like speaking. Okay, so Dan's asking, what use might you have for satellite data that's available, particularly things like sea surface height in the Bellingshausen Sea? Is that useful?
Yeah, so we do have some work that's just starting now in collaboration with Susan Howard and Laurie Padman, who I think are on the call today, which is to look at whether we can see modulations of sea surface height close to the coast. And I think I'm going to touch on this pretty quickly in the next few slides, which is we're not doing this via remote sensing, but actually looking at the hydrography. But we do believe that there will be a signature there in sea surface height. And in fact, maybe I should just keep an eye on this time. I'll keep going here, but I thank you for people adding questions to the chat here, and I'll definitely get to them at the end of the talk. Okay, so I want to now move to looking at the dynamics that are happening near the coast. And again, I think this gets to Steve's question. We know quite a bit about the circulation features in the West Antarctic Peninsula. So here's a nice schematic from a review paper by Carlos Moffat and Mike Meredith. We can see the fronts of the Antarctic Circumpolar Current offshore. We know that this warm water gets onto the shelf via the major troughs in West Antarctica. And we know that there is this second boundary current, which Moffat called the Antarctic Peninsula Coastal Current. I'm just going to refer to it more broadly as the Antarctic Coastal Current. I think it's the same thing. That goes in opposition to the ACC, and so in this region back towards the south. And this is very much a freshwater-driven boundary current. It will certainly respond to changes in the wind stress. So Ekman convergence or divergence away from the coast will modify sea surface height and change the strength of that current. But the frontal structure is very much driven by freshwater. And so this is a really nice section that was collected by Moffat and colleagues along the West Antarctic Peninsula here, shown by this black line. If you look at the salinity section, this wedge of relatively buoyant fresh water near the coast that gives rise to quite narrow and vertically sheared southward boundary current in thermal wind balance. The coastal current is well documented in various parts of Antarctica, especially in the Weddell Sea, there is less evidence of what this current looks like, say, in the Bellingshausen Sea, and the degree to which it actually can connect different regions of Antarctica. And so to address that question, we don't have a lot of ship-based hydrography in the Bellingshausen Sea, but one resource we do have are instrumented seals. And in fact, at least through the period of 2007 through 2014, this was a region that was very heavily observed by instrumented elephant seals. And I'm showing sort of the distribution of the hydrography here. This is a data set that we have looked at in the past, but we went back to this and realized that you could actually do some very interesting work in terms of making either composite sections or actually just looking at mean properties on, for instance, different density surfaces. And so I'm going to go through some of this pretty quickly, but this is just an image of what you can do with this data set. One can make maps. This is actually looking at the density surface that sort of separates winter water from polar deep water. You can look at the distribution of temperature and salinity on these. And you see a pretty dramatic signature as you move along the coast, that you have a signature of waters cooling and freshening as you move along this coast. And I'm going to argue in a minute that this is modification of waters as they are propagated along that boundary current via the Antarctic Coastal Current. But one of the important things you can do with that hydrographic data is you can generate a map of dynamic height. And so this is sort of equivalent of looking at variations in sea surface height, but you're doing it from actually measuring the density structure in the water column as opposed to just the height at the surface. And so what I'm showing here is a map of dynamic height where the gradients in dynamic height are tied to geostrophic speed. And so in particular, where you have higher values to your left, that's the direction of the flow. And so you can see that there's a signature of a strong gradient and dynamic height all along the coast throughout the Bellingshausen Sea. Here's the Latates Trough, here's the Belgica Trough. And we're arguing here that this is a signature of the coming down from the West Antarctic Peninsula and flowing along the face of all of these ice shelves in the Bellingshausen Sea. As I said, you can also take the seal data and you can create, as you would do via ship, a hydrographic section. These are composite sections. So this was work led by Ryan Schubert, who is, again, a master's student at Florida State. He collected profiles in these various bands, binned the data as a function of depth and distance away from the coast, and made these really beautiful sections of temperature salinity. And I'm not going to go through all of these, but again, the focus here is what's happening very close to the coast. And again, if you look, this is going from east to west all through the Bellingshausen Sea. In, say, a few tens of kilometers near the coast, water is flowing through the southern part of the Bellingshausen Sea and becoming colder, and it is also becoming fresher. So as we move down or progressively to the west, you see that that water is getting fresher. I think one of the things that I was more interested in, or I think has received less attention, is that, not only is the TS properties changing, but remember that this impacts the density structure as well. And so these black contours are showing density, and you can see that there is both a deepening of the density structure and an enhancement in the vertical stratification as well. And so these changes in the density structure will be tied to the circulation via geostrophic balance and thermal wind. And what we're able to do with these composite sections is actually look at the geostrophic transport in that coastal boundary current. And again, we did this by looking at the density structure, referencing to a level of no motion. So in particular, in this plot, we used a level of no motion of 400 meters. I'd be happy to discuss some of the assumptions that go into choosing that level of no motion. But qualitatively, the main result here is not sensitive to that. And the main result is that as you again move progressively from west to east throughout West Antarctica, there is an increase in the transport of the Antarctic Circumpolar Current. And so our argument for why this is happening is that as the Antarctic Circumpolar Current moves past each of these ice shelf faces, it is entraining meltwater coming out of the ice shelf cavity. That is doing two things. It may actually contribute some volume flux to the coastal current itself, although we suspect that that volume flux is pretty small compared to the transport. What it's really doing is modifying the density structure and thus changing the strength of the geostrophic flow along the coast there. And so again, this gets back to this three-dimensional interaction between what is essentially a zonal boundary current or coastal boundary current interacting with the overturning relation that is being supported by the troughs and the ice shelf cavity. And so I will again, sort of this picture that the Antarctic Coastal Current may enable connections between the different shelf seas, and in particular will be interacting with ice shelf melt rates, suggested this idea that the Antarctic Coastal Current may help to transport or carry signals of remote perturbations throughout West Antarctica. And so in just the last 5 minutes, I want to get to some recent work that is currently in review, which is to think about this idea of remote forcing of the continental shelf, and in particular what's happening at the coast, impact melt rates of ice shelves throughout West Antarctica. And the way that we've gone after this question is to use a numerical model. So this is work in collaboration with Mar Flexus and Michael Schadlock. We are using one of the many really insightful numerical models that Michael has developed over the years. This is a relatively high resolution simulation. So it's about 3 kilometer resolution, but it does have ice shelf cavities and an interactive ice shelf melt rate. So as either the temperature of the circulation and the ice shelf cavities change, the melt rates change as well. And so we are essentially doing a process-based study or a suite of sensitivity studies where we are a certain amount of freshwater perturbation that is only at the northern part of the peninsula, mostly focused along the coast. And part of the motivation for this is that, I don't have a slide to talk about this, but if we look at warming trends throughout Antarctica, where we're seeing some of the largest signals, and in particular, earliest signals of warming around Antarctica, it is principally concentrated around the Antarctic Peninsula. So this may be a location where you would expect to see some of the first signatures of changing climate, and in particular enhanced freshwater flux into the ocean here. And as I said, doing here is just looking at a series of perturbations. And so I'm just really showing changes here that are happening for one experiment that I will absolutely admit is a relatively large hammer. We're adding about 10 meters a year of fresh water in that yellow box that I showed on the previous slide. Although qualitatively, as I'll show in the next slide, the results are pretty similar regardless of the magnitude of the freshwater perturbation. And what you see here is, if I look at the difference between the perturbation and the control, when you add fresh water at the Antarctic Peninsula, we see a change, in particular here in sea surface height, that happens all throughout West Antarctica, the West Antarctic shelf seas, and is principally confined to the coast. So there's a propagation of this perturbation throughout West Antarctica that is carried by the Antarctic Circumpolar Current. And in this case, where you induce more inject more fresh water, it leads to a strengthening of the Antarctic Coastal Current, both in terms of a sea surface height gradient, in terms of its velocity, but also in terms of the density gradients that I saw, both a horizontal and a vertical density gradient. And if I look at the changes in salinity, we see that there's also evidence here, especially throughout the Bellingshausen Sea, that perturbation gives rise to a freshwater anomaly that, again, is very much confined to the coast. And so I think the most striking result from these simulations is that when we add this perturbation, we see changes in the melt rates of the ice shelves throughout all of West Antarctica, where as we increase the strength of the freshwater perturbation, the melt rates increase. So what I'm showing here is in these top panels, time is on the x-axis. So these are simulations that have run for a couple decades. On the y-axis for this particular panel is the average basal melt rate for all of the ice shelves in West Antarctica. And the colors here are indicating progressively stronger freshwater perturbations at the Antarctic Peninsula. And you can see there is interannual variability, but there is an offset as we add more freshwater that is almost a linear relationship between the freshwater input at the peninsula and the mean basal melt rates. We can also look at this at individual ice shelves. So here's Venable, here's Pine Island Glacier. They have their own sort of characteristics, which is probably largely due to the bathymetry in front of and within the ice shelf cavities. But qualitatively, the picture is similar. That as we increase the perturbation, the Antarctic Coastal Current strengthens, and we see an increase in the basal melt rates. There's one quite interesting feature here in Venables that at low melt rate, or sorry, low freshwater perturbation, the interannual variations in the melt rate are quite strong. So we have these large fluctuations in these red and orange curves. And as we move to stronger and stronger freshwater perturbations, we lose some of that strong interannual variability. And we believe and are sort of working on this problem that this is has to do with increasing the vertical stratification such that when you form sea ice in certain years, that we believe that this interannual variability is related to interannual variability in sea ice formation, that you're no longer, with an enhanced stratification, no longer ventilating that circumpolar deep water when you have convection in the winter. And so you're essentially stabilizing the water column and not punching down into this warm circumpolar deep water in these strong freshwater perturbation runs. And so this sort of gets to just about my last slide here, which is on the mechanism of what we think is happening. And we do believe that there is kind of two processes at play. One is the one I just talked about, which is you add more fresh water, you are enhancing the vertical stratification. So I'm showing that here depth, this is n squared. So this is just below the surface layer. This is essentially the winter water layer that I sort of started with during production. And you can see that as the freshwater perturbation increases, the stratification increases. And I think this is quite a suggestive plot that if we look at this, the difference in temperature between the pole and the perturbation at 300 meters depth, the changes that we are seeing in the temperature, we are seeing this warming all along the coast. They're very much confined to being close to the coast. We're not seeing large systematic changes or changes that are as large going all the way out to the shelf break. And so we believe that this control is largely due to coastal dynamics and not necessarily a change in the transport of circumpolar deep water across the shelf break. And this is just sort of the last plot to show that we can link the changes in freshwater input at the peninsula to the heat transport that is actually across the ice shelf face. So here we've drawn a section. This is for Pine Island Glacier. This is for Venable, actually showing that as you change the freshwater perturbation at the peninsula, it actually changes the flux of heat into the ice shelf cavity, which is then correlated with the increased basal melt rates. And again, as the freshwater input increases, that transfer of heat coming into the cavity increases. And so we see this as a change in the partitioning of the heat, either being lost vertically through convection when you make sea ice goes into the ice shelf cavity. So I'm just about out of time. I want to conclude with maybe one last slide here that I think comes back to the motivation at the beginning of the talk. I'm showing here the title of a really short essay that was in Nature, gosh, almost 15 years ago now. But this was a short paper that I think was pretty influential in my thinking about the overturning circulation when I was working sort of more focused on what happens in the Antarctic Circumpolar. And this paper came out in a time when there was a lot of focus on the dynamics of what's happening in the ACC and how that impacts the overturning circulation. And Martin Visbeck wrote this paper, which I call the push or pull paper, which was saying, you know, traditionally we thought of the overturning circulation as being this push of North Atlantic deep water down into the deep ocean. And there was this rather passive response, which is that mixing in the interior lifted that warm water back up. And that was sort of the picture consistent with Monk's abyssal recipes. And as we began to learn more about what happens in the Southern Ocean, and this idea that you have adiabatic upwelling across tilted density surfaces, there's a certain degree by which the overturning circulation can be governed by a pull, as you pull that deep water up to the surface of the Southern Ocean, and ultimately the push of deep water down and the pull of that deep water back up, they have to balance via water mass transformation. And I would argue that we've been thinking about the shelf overturning circulation somewhat in a similar way, that a lot of the literature thought about how much warm circumpolar deep water are we pushing onto the shelf at the shelf break. And I'd argue that there is an equal role for the idea that melting of ice shelves and the transformation it does can pull water onto the shelf and have an equal role in driving at least the steady state structure of what an overturning circulation looks like over the Antarctic continental shelf. And so I think that's one of the focuses of some of our work going forward. We have a range of different numerical models, some quite simple like the one I'm showing here, that are trying to sort of tease out what are the various controls that drive the volume transport of the overturning circulation on the continental shelf. And again, in a steady state scenario, there has to be agreement between the volume flux coming in at the shelf break and the transformations that are happening either in the ice shelf cavity or in front of those ice shelves. And I would argue that there's still a lot to learn about the controls close to the coast and how we can represent them optimally in coupled climate models. So leaving sort of everyone with that thought, I will just leave up here a summary of kind of the two main conclusions of what I talked about today, and be happy to take any additional questions. Thanks for your attention.
Thank you very much, Andy, for a fascinating talk. We still have a couple of questions from the sort of halfway break. I think you answered Jeff's question, which was about seal data, but Olga's question perhaps is interesting. Olga, are you still with us? Is there a chance you'd like to?
Sure. Fantastic talk, Andrew. Thanks a lot for it. So my first question was about the depths at which the meltwater comes out.
Yes, I think I could open.
So it's about, you don't observe it nowhere deeper than the ice shelf draft. So effectively it just slides along the ice shelf draft, and it does not come out somewhere, say, because as actually this cartoon, the bottom one shows, there is a deepening of the draft towards the grounded line, but you do not observe melt flow at those kind of depths. It's always at the ice shelf front depths, at the ice shelf draft at the front. Is that correct?
Yeah, that's right. I don't know if I can go back here quickly. There's definitely a spike or a maxima in the meltwater concentration that is well correlated with the depth of the ice shelf face, at least here in Venable. You can, if you look here, I mean, it's certainly true that the meltwater concentrations are not zero below that, and there's some spread along there. The degree to which this is, water being detrained from a freshwater plume in the cavity and spreading out at those density surfaces, it's not clear. A striking feature of this that I did not really talk about, Station 37 was within a couple kilometers of the ice shelf face. And if you actually were to just look at this profile, you can sort of see it here. There's one meltwater maxima at 350 meters. There are others at shallower depths. And if you were to look at the profiles in these stations, you see the signature of thermohaline intrusions. And so I think it's pretty clear here that there is some meltwater that's getting out. It's buoyant, it convects vertically, and then starts to shed eddies or just form intrusions at different depths. But I think to answer your question, if you look further away from the coast, there is some meltwater at deeper depths, but it gets weaker pretty quickly. The other thing I will say that's related, there is quite a bit of, I think it's evident from these profiles that there's quite a bit of recirculation in these troughs as well. So whereas I sort of sketched this picture of the water being delivered out to the shelf break and very much concentrated there, I think that is some fraction of the meltwater getting out. And some of this meltwater may recirculate for I don't know, many years before it is ultimately leaves the Bellingshausen Sea, leaves the shelf.
And yeah, thank you. And if I may, another question on the second part.
Mhm.
So the propagation of that perturbation, again, it is more or less confined for the upper, 400 meters? It doesn't go deeper. Is it correct?
That's what it appears in this data set.
Okay, so once again, it doesn't go nowhere near the grounding line and anything in terms of the depth. So it is kind of intermediate depths of the water ice shelf draft.
I think that's right. I will be honest, and off the top of my head, we probably want to go back and look at what the, have geometry of Venable ice shelf looks like and how deep is the grounding line of the grounding zone. And if you're interested, I'd be happy to go back and look at that in a little bit more detail.
Well, it's all right. Thank you. Yeah, it's kind of the order of magnitude. That's good enough. Yeah. Thanks a lot. Okay. Fantastic. Thank you.
Thanks, Olga.
Thanks, Olga. It looks like Jeff Ridley has his hand up. Do you have a question, Jeff?
Hi, Andy. What did you look at the barotropic stream function of in the Ross Gyre? I presume you couldn't look at that with the hosing experiment because you.
Yeah, so that's a thank you, Jeff. That's a really interesting question. No, so in the hosing experiment we couldn't because here's the model domain, and we essentially, or Michael does this, sets the boundary conditions. So this model is using boundary from the echo model. And so both the temperature and salinity and the velocity field are set to bound. So there is not really, there's not a lot of freedom for the Ross Gyre because you would sort of just have the eastern, you can sort of see with the bathymetry here, this would be the eastern edge of the Ross Gyre. There's not a lot of freedom for that to evolve in response to perturbations on the shelf. But I think that's a really interesting question, that if what I've sort of argued here is dynamics close to the coast, feed back to the shelf break, that changes the boundary current structure, which ultimately forms the southern boundary of the Ross Gyre as you get far enough to the west. And I think it's absolutely possible that there could feedback both from the gyre onto the shelf, but from the shelf back to the gyre. And that's something we've not had a chance to look at in this study. It is somewhat related to work that is being led by a postdoc in my group at the moment, Earl Wilson, who has been doing some more idealized work on sort of interactions between the ACC, subpolar gyres, and the continental shelf and slope.
All right, thanks.
Thanks, Jeff. Do we have questions from the group?
Sure, I'll ask a question. Laurie Padman. So you said that for the hosing experiments, the numbers were quite large,
Mm-hmm.
But you gave a range of results for much smaller values.
Yes.
If I look at the top plot, the interannual variability that's there anyway is of a similar magnitude to the hosing experiments. So is there any relationship between the magnitude of your hosing experiment and what's really going on in the real world? That might be causing the true looks like decadal variability in that plot.
Okay, so okay, so yes, one can see some signature here. If I integrate over all of the ice shelves, you see this decadal scale variability. Is interesting that one can maybe see as the similar structure in Pine Island and maybe not so much in Venables, which speaks a little bit to the uniqueness of the circulation around these different ice shelves. Let me make sure I'm answering the right question, Laurie. Are you asking whether what you're seeing here is just the interannual variability in the forcing may explain some of these changes?
Well, I'm asking a couple of things, I guess. One is whether freshwater variability roughly in the area that you're considering for hosing, whether that is a forcing that's appearing in the real world, or whether maybe this is all just wind and not freshwater.
So that's right. I absolutely agree that the wind forcing can have maybe an equal impact, maybe potentially a stronger impact. I think what we're looking here is the mechanism. And in terms of whether this freshwater forcing is going to be large enough to actually see this signature, as I mentioned, we were certainly motivated by this idea that, we have seen increased warming at the Antarctic Peninsula. As we began to dig in, as we've actually talked about a little bit before, it's not evident that we are seeing very strong meltwater fluxes over the last couple of decades into the Antarctic Peninsula, whether it's from runoff or melting of ice shelves. We have then gone on to look at sort of the predictions from various IPCC class models, and the suggestion that is in the next couple of decades, almost all of the models predict increases in the freshwater forcing that are actually maybe not as large as some of these largest ones, but are in the range of, say, 5 meters per year. So I think in terms of understanding this mechanism, I would argue that in future decades, where maybe today, the wind forcing is the dominant process that's giving rise to the inter variability we're seeing, but that this mechanism writ large across West Antarctica may become much more important in the future. But on a ice shelf by ice shelf basis, I do think the stratification in front of these ice shelves is still very important and not well understood how this can vary from season to season or even from year to year.
Okay, thanks.
Yeah, thanks for the question.
I'm intrigued by the relationship between the basal melt rate and the freshwater input. Mm-hmm. I noticed that relationship seems to level off as you go to higher forcing. Did you look into or have a sense of why that is the case?
So why? Sorry, say that again, Craig.
Why is the relationship leveling off at higher forcing?
Yeah. Well, so I mean, we are kind of continuing this work. I mean, that we did some preliminary budgets, but there's still kind of a lot to understand here between this coupling between what's driving the geostrophic flow and what's governing, say, heat fluxes. But what's happening here, I think what you're seeing two fates, right? It can flow into the ice shelf cavity, give off that heat to the ice shelf, and then flow back out, or it can lose that heat vertically through the water column and ultimately to the atmosphere. It can be ventilated by convection. And so what I was trying to say before is those years where you see a lot more interannual variability, I think those are some years where there's stronger sea ice formation, you have more convection, you ventilate more heat to the atmosphere. And so as I move to stronger and stronger forcing, as I increase that stability, it just means that at some point that heat is all flowing into the ice shelf cavity. And as I make the stratification stronger, you've essentially weakened or suppressed that vertical heat flux or the ability to ventilate that heat to the atmosphere as much as you can. And that would be one explanation for why it starts to flatten out or saturate, if you will.
Thanks.
Yeah.
Do we have any further questions, perhaps final questions? We're a little bit over time, and I see quite a few people are rushing out because they've got probably other meetings and things. Thank you so much, Andy, once again for speaking. It's a wonderful contribution to the series. I look forward to putting it up online.
Great. Thanks, Greg. I appreciate everyone's time, and thanks for the questions.
Thanks, everyone, for joining us. I hope you have a great rest of the day.
Okay, bye.
Cheers.